Hello, my name is Vassili Salaou, and I will present you a joint work with my colleague, Christelle Loyudis from Naval Labs Europe on a preprocessing speed improvement for the trip-based public transit routing algorithm. When we speak of public transit, we refer to a network combining scheduled transportation modes and walking transfers between the stops. We call a trip, in this context, a sequence of arrival and departure times of public transit vehicle at its stop. For routing in public transit networks, two important criteria are the earliest arrival time, if you are given a desired departure time, and the number of transfers. We are interested in computing the Pareto front and one solution per element in the Pareto front, which we will call a complete set of solutions. Unlike many big criteria shortest path problems, this problem can be solved in polynomial time. For real-life instances, however, using classical graph algorithm will not be efficient enough for real-time response to user queries. Hence, some dedicated techniques have been developed for that type of network. This is not an exhaustive list, of course, but I will cite transfer patterns, which is the fastest technique but relies on very heavy preprocessing, Raptor and connection scan algorithm, which are both based on timetable information without any graph representation, and the trip-based public transit routing algorithm that we will discuss a bit later. There are also some more heavy preprocessing algorithms like HyperRaptor or Accelerate Connection Scan, which relies on partitioning of the public transit labeling, or condensed search tree, which is an extension of the trip-based public transit routing. All those got heavier preprocessing, but are running faster than their original versions. In this talk, we are interested in integrating real-life information with frequent network updates. A first remark is that the timetable is nothing more than a prediction of arrival times and departure times of vehicles at stops. Many things can make it incorrect. For instance, congestion, crowded vehicles, or accident can create some delay. But of course, you can also get some modifications of the structure of the network, like a stop being removed. Basically, if you want to be able to compute a complete set of solutions, you have two choices. Either you rerun the preprocessing each time you get an update, or you modify your preprocessing phase so that it can deal with some delay models or change of structure. In this talk, we consider one algorithm that can be fitted for the first option, that is rerunning very frequently your preprocessing, and it is called the trip-based public transit routing algorithm. It has been proposed by WIT in 2015. This algorithm is based on a representation of a public transit data where the trips are the nodes of a search graph and the transfers are the arcs. In this graph, all you have to do is to take one additional trip at each iteration and performing a classical breadth first search exploration in order to find the complete set of solutions for all 12 criteria. In order to build the search graph, you will preprocess the public transit data. The first remark is that you need only the earliest trip for each transfer between a trip and a destination line, because it is sufficient as you are minimizing the arrival time. A second remark is that you can prune some transfers and still be able to compute the complete solution set. WIT proposed a preprocessing that performs this type of pruning based on arrival times, and compared to a non-pruned graph, it significantly reduces the number of arcs and improves the speed of the queries. So let's see a bit how it works. So first, you can generally remove a transfer that only brings you backward. What I mean by that is that if you are transferring from this trip T here to this trip Q, well, you're only getting back to stop S, taking this transfer. So it's quite unlikely that you will improve the arrival time here. So most of the time, that type of transfer can be removed. And there are a lot of them. since lines are usually both ways. Then you've got pruning that is based on arrival time. So the idea is that you will look at all the transfers from trip T, all the feasible transfers, starting by the transfer from the latest stop of the trip. And you will mark with the earliest arrival time and change time all the stops that you've reached taking the trip T, all the stops you've reached taking the trip U, and all the stops that you reach walking from those stops. Then, if you've improved any value of any stop, you will keep the transfer. On the other hand, if you cannot improve any of the arrival time at any stop, then the transfer will be removed. So the total preprocessing duration is directly linked to the number of transfers to check, obviously. That is why we proposed this first preprocessing step, in order to reduce the number of transfers that we would get to the arrival time-based preprocessing. So we call this additional step line-based pruning because it's based on transfer from line to line. First, we need to define exactly what a line is. So each line is an ordered set of trips. The idea is that you will group into a line only trips that have exactly the same stop sequence. Then we will also need to be able to order the trips of a line. The relations lower or equal and lower basically mean that it is not possible for two trips of the same line to overtake each other. If such trips with the same stop sequence exist and are not comparable, they will be put into different lines. The idea of a proposed preprocessing step is to look at all the transfer from a given trip to one destination line together. So first remark is that you can also do some U-turn pruning at the line level. Obviously, here is the transfer duration is higher than the transfer duration here intra-station. Then you can never improve by taking this U-turn transfer. So you can most of the time remove all the transfer at the line level. Now, if you look at one given trip T and you want to look at all the transfer to a line L prime, well, as before, we will sort those transfers. So first by decreasing origin index and then by increasing destination index of the stops. So it gives us here 1, 2, 3. So if we look at this first transfer, well, V is the earliest trip that we can get performing this transfer from T. And we mark all the later stop with V. Then we look at the second transfer, but we can't improve here, getting, for instance, exactly the same trip V as the earliest trip. So we can safely remove this transfer. And then suppose that for the trip, for the transfer 3, you can get an earliest trip U. Then in that case, you will keep both transfer 1 and 3. So basically, what is important is that this transfer set is still correct. It still enables you to compute the complete solution set. So to see that, you can take any optimal solution and check its transfers in order. If it contains any transfer that is not already in T, then you will be able to replace it by another transfer in T. Because like your transfer 2 in the example, it has only been removed because the transfer 1 enabled you to get at this stop with the same trip or an earlier trip. So you modify your solution this way, and in the end, you've got only transfer of T and exactly the same arrival time. Now, to assess our modification, we've tested our implementation on 3 datasets. So the first one is covering Netherlands and is provided by OV API. The second one is covering Île-de-France, which is the urban region around Paris. And the larger one is covering the whole Korea and is a proprietary dataset that has been provided us by NeighborMap. The other 2 are open datasets. For all those 3 datasets, we added additional transfers between stops as long as they were at least 600 meters one from the other. So it makes our footpath a bit larger than you usually find in the literature. So we propose to test 4 different prunings. So the first prunings, there's no pruning at all. So we keep all the feasible transfer. We test the line-based pruning separately, the arrival time-based pruning separately, so that is the one that has been proposed by WIT, and the combination of the 2. So the line-based first and the arrival time-based second. First, note that the preprocessing time is relatively long in the no pruning case. That is due to the large amount of data generated that has to be put into memory. You can also remark that applying the line-based pruning before the arrival time-based pruning has little impact on the number of transfers kept. That is because in our implementation, the order of transfer checking is similar in both cases. Then, if you look at the mean preprocessing time, line-based pruning on its own is significantly faster than arrival time-based pruning on its own. The combination of the 2 is also faster than the arrival time-based pruning by a factor of 2.45 for Île-de-France and Korea, and by a factor of 1.4 for Netherlands. Note also that for the Korean network, well, the network was too big to redo the preprocessing every 5 minutes, for instance. But with the proposed modification, we can do updates every 3 minutes, which is already quite frequent. As for the queries, we use randomly generated pairs of origin and destination stops. Note that the query time includes the building of a solution. Since the search graphs are quite similar for arrival time-based and line-based plus arrival time-based, we have very close mean query duration for both preprocessing methods. However, it's interesting to note that the line-based preprocessing on its own yields already some significant speedup, as it divides the query time by 1.5 for Netherlands, by 2.9 for Île-de-France, and by 3.4 for Korea. As a consequence, if preprocessing time is really an issue, for instance, for a very large network with very frequent updates needed, you could use it directly as an alternative to complete preprocessing. So to summarize our results, first, the proposed preprocessing keeps the optimality of the search phase. Second, it can be used both alone and in combination with the preprocessing proposed by WIT. Third, the tests that we performed on 3 larger scale datasets show that the method helps reducing the total preprocessing time and can help making possible very frequent real-time updates on large networks. As a perspective, this faster preprocessing might be combined with feature additions or customization of the search phase in order to help limit the preprocessing time, as those additional features might require more preprocessing. Another remark is that the other option to take into account real-time updates, that is modifying the preprocessing to make it compatible with delays or change of network structure, could be looked into for the tree-based public transit algorithm. For example, in a context with you need very frequent updates, or more customized search phase. That's the end of my talk. I thank you for your attention.